Hi, I'm Koby, and I'm a member of the Charger Active Defense Team 1. Defensive cybersecurity tools are almost all passive in nature, simply focusing on blocking incoming attacks. What is needed is an active defense mechanism that is capable of disrupting ongoing attacks to prevent them from continuing. Our project focuses on determining if a fuzz testing workflow can be developed to discover active defense responses capable of hindering an ongoing attack.
Hi, I'm Nick. What is active defense? It is a defensive cybersecurity technique that is used to disrupt an incoming attack from an offensive cybersecurity tool. To do this, we want to use fuzz testing. It is a software testing technique that injects invalid inputs into software to test whether they might crash or hang or find any bugs or vulnerabilities. If we can perform fuzz testing on offensive cybersecurity tools over a network, we think we can find active defense inputs that can be sent back to offensive cybersecurity tools to disrupt their attacks.
The main deliverable of our project is the fuzzing workflow. Our goal in creating this workflow was to outline steps that can be applied to an offensive cybersecurity tool to discover active defense responses for that tool. So the first step is defining a scope. This entails choosing an offensive tool to apply the workflow to. The second step is selecting a fuzzing tool. So a fuzzing tool with the ability to fuzz over a network is an ideal choice, as you want any weaknesses found in fuzzing to be able to be sent back across the network. Certain tools have compatibility restrictions or can be designed for very specific use cases, so it is important to thoroughly analyze the fuzzing tools to ensure that they are appropriate for your use case. There is also the option of developing your own fuzzing tools. Large language models are capable of creating fuzzing tools that are tailored to specific protocols or specifications. You also need a way to store the packets being sent by the fuzzing tool so that the effects can be repeated for testing purposes. The next step is setting up an environment. It is recommended that all fuzzing and active defense response testing be done with virtual machines connected to a host-only adapter. This prevents potentially harmful traffic from leaking out into an external network. The fourth step is analysis of the offensive tool. This can involve performing static analysis with a tool like LDRA or simply going through the tool source code. This can reveal potential weak points within the program that can be targeted during fuzzing. The next step is fuzzing the offensive tool, and we recommend setting up your fuzzing tool in one VM and your offensive tool in another. The next step is testing any potential vulnerabilities found during fuzzing. Any packets sent by the fuzzer that cause the offensive tool to crash or hang should be sent to the offensive tool outside of fuzzing to determine if the effects are repeatable. If the crash or hang occurs outside of fuzzing, then an active defense response has been discovered. And step 7, any active defense responses should be analyzed for further insights into other possible vulnerabilities. And then in the last step, steps 4 through 7 can be repeated to try to discover more responses in the event that some old exploits are remedied in updates or patches to the offensive cyber tool.
Now let's look at using the fuzzing workflow on an example program. This is the FTP brute force tool generated by the Claude large language model. So let's define the scope. An FTP brute force tool works by sending different combinations of usernames and passwords to an FTP server and looking at the server responses to determine if they are correct or not. It is made entirely in C++, which makes it possibly vulnerable to some memory issues due to C not being a memory-safe language. Now, in selecting a fuzzing tool, we look at what is being fuzzed. In this case, it's the tool's ability to handle their server responses. So we want a fuzzing tool capable of sending those out. That is why we're creating our own, because there's currently nothing on the market that does that. We set up the environment in host-only mode using 2 VMs. And when analyzing the selected offensive tool using static analysis, we were able to find a possible buffer overflow. When we configured our fuzzer to look for this, we were able to confirm that there was in fact a vulnerability for this.
On the left, you will see our Python active defense service currently running on port 555. On the right, you will see the terminal I will use to execute the file transport protocol brute force attack. You can see when it is ran, the active defense service responds with an active defense, causing the program to hang. I will now show you a demonstration of the URL enumeration tool being deployed against the same active defense service. You can see that this causes a segmentation fault when an active defense is sent to it.
In conclusion, we sought to prove the feasibility of performing active defense by fuzz testing offensive cybersecurity programs. We created a fuzz testing workflow that outlines how to do this, and we have applied it to real programs.